A photovoltaic panel is at its peak production when it receives direct sunlight perpendicular to the panel. Manufacturer data is taken from optimal laboratory tests and recorded as the maximum values. When I was studying, panel prices were moderate and they had to be installed as optimally as possible. Remember that in winter the panel must be installed at a steeper angle and in summer at a shallower one. There were also, and still are, trackers, a motorized structure that follows the sun like sunflowers to get every bit of energy out of it and thus amortize the installation better and more quickly. Nowadays, panels are so cheap that installations provide such a high profit margin that even the installers make a good cut. And there's no longer a need to spend money on following the sun. They are placed at a fixed tilt. The degrees are an average of winter and summer. They also add more panels to cover, even just for aesthetics. Although there are areas where the sun doesn't hit all day, as long as that panel or those panels in shaded areas don't create a bottleneck in a series connection. These are installations where we no longer look at, we're really going all out. So that's fine. I think that's great. We're euphoric, yes, but that doesn't change the numbers. Panels are cheaper, but in the shade, they don't generate even half the power. I'd say not even 25% of their maximum power. And I think I'm being generous, but you know that saying I believe, maybe, perhaps, more or less. No. Numbers. And in this video, we are going to get those numbers. Right. A panel approaches its maximum when it's facing the sun directly without obstacles, and the panel is clean and perpendicular. That's clear. Then, a lower level of power, less power, would be a cloudy day. Not too much. If the sun is perpendicular, but it's slightly cloudy, it will still be close to its maximum produced power, and so on, down to clouds that let very little light through. But it produces more power than a panel in dim light or shade outdoors. The next level would be inside a room, inside the house, until it gets darker and darker, and finally covering the panel completely. Well, here I am inside the house, see? The house lights inside. I use this spotlight for recording. The panel is here, inside with house lights, okay? 8 volt. It doesn't reach 9 volts. It doesn't reach 9 volts inside the house. Let's check the short circuit current. We're talking about it does not even reach 9 milliamps. 9 milliamps inside the house with the recording lights and the indoor lighting. These conditions could power 3 LEDs in series. Increasing the surface area of panels in low production zones to compensate seems fine to me, considering the money invested and the power it will produce. My professor and I were consulted for a very optimistic project, and when I said that all that glitters is not gold, they did not take it as reliable data. And I agree. I am a numbers person too. Things must be measured. I have a friend who used this as a slogan at his company: what cannot be measured cannot be improved. A solar panel is made of cells that are diodes, which, if light hits them, that is, electromagnetic waves in a frequency range around visible light, generate a voltage drop that can be harnessed to produce electric current. So, as soon as it receives any light, the tension or voltage is going to be achieved quite easily. Then the current or the juice, the power, is achieved with the amount of light or the lumens. The minimum voltage I have recorded is at night, logically at night, when I had to connect an old panel of my cousin's, and I was not sure which was positive and which was negative. It gave me values. It gave me a value of less than 100 millivolts, or 0.1 volts. And we used a flashlight to force it and raise it a few more millivolts. So to be sure to identify the positive and negative cable and leave the installation connected that same night. Then the next level is in my living room, which, as you have been able to verify, has not exceeded 9 volts. And whenever I have measured inside the house, I have never achieved more voltage or amperage, and consequently more power. And now I am getting ready to do the amp hour or milliamp hour test, or whatever you prefer to call it, kilowatt hour, microamp hour, nanoamp hour. Whatever you want, it makes no difference to me. From the 150 watt panel facing north, meaning always in the shade. Indeed, the panel is 150 watts maximum, 18.5 volts maximum working voltage, maximum current 8.12 amps, and 8.77 amps of short circuit. Before putting on the milliamp hour meter, I am going to see the values I get here in the shade. Let us remember that the maximum open circuit voltage is 22.8 volts, and we see that it is providing 21.72 volts. But do not worry, that is normal. As I said, voltage is achieved very easily. The short circuit current now gives us 1.37 amps. That does surprise me a bit. I thought it would not exceed 1 amp. Now, to set a proper load, that is, to count the milliamp hours, I use my rheostat and I start reducing the resistance until I get a voltage drop on the load of 12 volts. Slightly above 12. And I'm measuring the resistance I've been using, and it gives us 12.7 ohms. Now I'm going to use my milliamp hour meter, which you've seen in other videos, but I have to power it externally so it always works. It accepts 6 to 30 volts. I'll power it with an external 12 volt source. The resistor I'm going to use isn't 12 ohms. I'll use this 10 ohm one that handles up to 100 watts. We won't be exceeding 15 watts. It's fine. The external source will always keep the meter powered at 12.5 volts. Always. Well, for the duration of the test, which is 24 hours one day, since the resistor we installed isn't 12 ohms, but rather 10 ohms, the drop is 9.3 volts. But I don't mind. This way you see I'm being generous, and the milliamp hours I'll provide will be kind. They'll be high-end figures. Well, we can see the meter already tells me the voltage drop is 9.34 volts. 0.9 amps are flowing, that is 900 milliamps, and the dissipated power is 8.5 watts. I started the test at 1400 hours on the 12th. It's a splendid day, a very sunny day, and even though the panel is in the shade for the test, keep in mind that this test is being conducted under the most favorable conditions. I didn't mention it, but the resistor is very hot to the touch, so let's measure its temperature. It's over 70 degrees. Careful. At 5:30 in the afternoon, you can no longer harness the energy. Well, unless we have a very efficient MPPT controller, like say, a switching power supply that could take advantage of those 0.3 watts. I mean, nothing. For the curious, when I measured a panel at night in total darkness, I'm going to measure it with a voltmeter on a very small scale. It's 9:20 at night, beautiful night, darker than the future of some. Well, 24 millivolts, that is 0.024 volts, and a short circuit current of 3 microamps, that is 0.003 milliamps, or 0.000003 amps. Good morning. Before breakfast, it is already 8 in the morning the next day and nothing. There is no power. This just doesn't work at these hours. The time it shows of 5 hours and 16 minutes is the time that measurable current has flowed. The device measures the time it is working. At night, if it doesn't flow, it doesn't count. It is the time it records as working. It has already accumulated 2,970 milliampere hours and 27,984 milliwatt hours, that is 27 watt hours. Since I wasn't exact at 2 in the afternoon for the start, but rather about 5 or 6 minutes had passed, I will also finish after 2 in the afternoon, just to be even more generous. Like that. Well, you see, favorable conditions, me being generous, values above, it's wonderful. What does the 12V 150W panel provide? Well, in the shade for 24 hours, 10,000 milliampere hours, that is 10 ampere hours, almost 116 watt hours. These values would have to be extrapolated to other panels' different power ratings and different voltages. Anyway, my conclusions on this specific 150 watt panel in the shade would be enough to charge a mobile phone, 2 mobile phones, perhaps, but taking into account the hours, 24 hours, all day to charge them. Not in 2 hours like we normally do with this charger at home, you know. Energy for 3 phones, I don't think so, because you also have to account for energy losses in the electronic circuit of the charge controller, and of course, a good sunny day. I say no, but anyway. Of course, panels that are in direct sunlight don't produce for 24 hours either, obviously, but if the same panel is producing 1 amp, approximately, in the shade and one in the sun is close to 8 amps, I can risk it with a margin of error. Whatever it may be, that to match the production in the shade, you need 8 times more surface area in panels. So, it is a matter of weighing it up. As I said at the beginning of the video, solar panels are very cheap. If it is for aesthetic reasons, complimentary, or marketing, or whatever you want, it is worth it. No issue. But if you're going to compete to maximize energy production per square meter, per square centimeter, pushing it to the limit, the shade gives you about 8 times less. You can criticize my conclusions, my opinions, even my methods, but not the data. And well, no need for me to tell you to subscribe, because that is up to each person.